The medium and small curved chisels. We're going to, this one here, the medium is the H13, and this is Mark's, which is a little different than mine. I did a flat chisel like this. You're going to use a narrow fuller and a wedge, just like I just showed, but it's going to be smaller swage, smaller fuller. And here's the H13 one that I did. I think I had it 5/8 of an inch wide, if I remember correctly, and then I had about a 5/8 of an inch swage, and then I tapped it on the edges, which was able to tighten that up a little bit. So you're going to forge it real thin. The whole reason why you're going to do H13 is you want it to be very thin and still hold up. And H13 is a hot work steel. That's what H stands for, is hot work category of steel. And so you're going to forge it to 1/16 of an inch, and then about 5/8 wide. I might have moved up to a 1/2 inch. You know, just you can try the larger one. If it's not a tight enough curvature, then you can just go to the next one, or you can work on the side like I did. And then you're going to finish with a grinder in this case, because H13 hardens in air. So if you let this come down to room temperature where you can handle it, your file is going to skate off of that. You're going to have no luck with that. If you have to file it because you don't have a grinder, then you're going to have to do that hot. In general, I try not to file hot because the teeth are fine. So the rule of thumb with files versus rasps is that rasps, if you rasp cold, then you pop the teeth off of your rasp. So you want to save your rasp and have it last longer. You rasp hot. Files, on the other hand, tend to wear the teeth down and clog the teeth really bad on hot material. So you want to file cold in most instances. This would be an exception where I wouldn't do that. So here is the piece already drawn out, and then I'm going to come through here and swage it. Now you'll notice it looks like it's kind of cold, but again, we have the real bright LEDs. This tool in particular, I want to stress that you cannot work it cold. So it looks cold in the video. It's on the very lower end of where you would want to even do it. And in fact, I would recommend you don't work it as cold as I do. I have a lot of experience with H13. There's still some color in there. You can see there's a little bit of a dark rose color. But I came back for another heat, and I'm working this back a little further. Now, at the end of this particular part of the video, you'll see that I'm turning it on its edge, and you can see that it's still got hot heat in it because of how easily you can see that material move. Now, H13 gets hard really quickly, so there is actually a little bit of heat in here, but there's not a lot. So, just bear that in mind. The problem with H13 is it's an air hardening steel. So not only do you have the problem of the blue brittle range, but when you get it down to around that blue brittle range with H13, that's the range that it's starting to form martensite. So one big problem with H13 that people do is they forge it too cold, and then that will set up stresses that will result in cracking and tool failure later. So now we're going to kind of do a little bit of an overview. We got to heat treat this, and I've been talking about that. So we're going to do an overview about heat treatment in general. So let's just talk about what we know about heat treatment. So iron is a solid solution. I put this in parentheses so that, for emphasis. And just like quick review of what that means. A solution is a mixture of two or more elements comprised of your solvent and your solute. So an example would be salt and water, and your water being your solvent. That's what the salt, which is the solute, mixes into, and salt water being the solution, right? Steel is iron with carbon. Iron is the solvent and carbon is the solute. So the carbon can dissolve into the iron, right? So that's why we're calling it a solution. Why does steel harden? Okay, steel hardens because, as Victoria mentioned earlier, in a normal state, let's just back up to what you would call like baseline state with steel. If you just let it cool gradually, it's going to form what's called perlite, and that's soft. That's what's happening when you normalize something, when you anneal something. You bring it up to temperature, you let it cool down slowly, and it's soft and stress-free. You know, it has carbon in there, but it's not distributed really evenly. Mostly you have the ferrite, that's the soft stuff. And then you got this other stuff called cementite, and mostly carbon's tied up in that cementite. So the structure of iron is this cubic lattice. You probably saw that on the chart that Victoria put up. And there's these couple of little cubes on there. They look like a 6-sided playing die, like, you know, you play dice with. So that's how carbon molecules arrange themselves. They arrange themselves on the lattice. And when I say molecules, I mean the atoms themselves, so the atoms of carbon. And iron and carbon can rearrange themselves on this lattice, right? So as it goes up into critical temperature, that lattice changes a little bit. And then depending on how fast you cool that, the carbon is either going to stay on that lattice or it's not. And what we want it to do is we want it to stay on the lattice. So I want to have a couple of visual aids so you can visualize this. If you want to know more about this, and I recommend that you do, you're not going to get everything that you need to fully understand this subject, you know, in a single talk. And, you know, there's a lot of terminology that you need to learn and some concepts. So I found a good site called msestudent.com. That's material science and engineering student.com. And it explains a lot of these really well. But I want to point out these little cubes because this is important. This is what's going on internally when you get this up to austenite. All steel, regardless of carbon, will do this. At room temperature, or when it's cooled slowly, it has an atom in the middle. And then when you heat it up to that critical temperature or that transformation range, you get thermal expansion, and all of a sudden some other iron atoms pack on. These are all iron atoms, right? And that's not really necessarily what's important. What's important is that carbon can pack on too while those extra iron atoms are packed on. So that's called a phase change. And at low temperatures, perlite is formed, and the carbon is less soluble in what's called alpha iron. That's the iron that's at room temperature or you know, is allowed to cool slowly. That's what happens when you normalize it. Anything below critical temperature, and it precipitates out and forms this thing called cementite. I know this is getting a little bit ahead, and a lot of this is just this is kind of like my math, right? You know, not everybody's a math person, but if you kind of want to fully understand this, it helps if you kind of at least get introduced to this a little bit. So all the carbon is in this cementite here, and it just looks kind of like cement under a microscope. That's why they named it that. At higher temperatures, you form austenite. The carbon becomes more soluble. So it's exactly what's happening if you have a glass of water and you heat the water up, then salt will dissolve more readily into the water. Well, you've changed the solubility of your water. And at higher temperatures, the solubility of carbon and iron changes, and carbon can diffuse out of the cementite, and it can go into the other parts of the steel. And you'll imagine that it probably takes a little bit of time for it to move from one place to another. And that's why you want to do your soak, because it takes a little bit of time for that carbon to diffuse. So getting back to that little cube lattice, this is your ferrite here. This is when you don't have any carbon attached at all. And these little gray guys, that's your carbon. You'll see that those are able to stick in here on these edges. So austenite, what's important about going from this structure, this body centered, where there's one atom in the middle, to this structure here, is the spaces get a little bit bigger or more available for this carbon. There's more places, and the carbon will start attaching and forming austenite. So it's going into solution, just like salt and water go into solution when you heat it up, or more readily. And then when you freeze it, it gets stuck. It goes back to this, but it gets stuck with these carbon guys on there. So that's the whole point of what you're trying to do, is you're trying to bring it up to where you have austenite, and that's basically making these sites available for the carbon to stick. And then you freeze it by cooling it down too rapidly for that carbon to go somewhere else. So just, you know, gonna do like a base, you know, a little bit, you know, of the heat treatment review. Normalizing and annealing is when you cool too slowly to make martensite. This is the hard stuff that you get from austenite. So normalizing and annealing, they do about the same thing really, but one happens over a longer period of time. This is if you insulate with like vermiculite or ash. So anyway, they're both forming perlite. And hardening has two components to it. You've got to heat it up to within the specific range. That's the critical temperature or transformation temperature where it makes austenite. And then you need to, there's a cooling factor to this. You need to cool that fast enough that it doesn't form this stuff, the perlite, and you want it to make the martensite. So tempering, you know, what does tempering do? Tempering degrades this martensite that you made, this real hard stuff. It starts to break it down and it actually starts turning back into perlite. But the cool thing about being able to temper is that when you're applying heat, you're applying it in a controlled way. You can apply more heat or less. And if you apply less heat, then you form less perlite. And if you form more heat, you'll form more perlite until all the martensite will go away eventually. If you temper too much, then you take all your hardness off, and you'll know that because you know not to, say, heat up the end of a chisel when you're grinding it on the grinder, or else it'll go soft. That's because you've broken down that martensite. So the cool thing about tempering is that you can take the same piece of steel, and that piece of steel could make a chisel that'll hold a real fine edge over a long period of time, but you know you're not going to try to pry open a paint can with it because you might snap it. On the other hand, the same piece of steel you could take almost all that hardness off, and you can make a spring, and you can put it on a truck and put a bunch of weight in the back and bounce it up and down the road for hundreds of thousands of miles, and it'll stay tough. So tempering is what allows you to do that, and that is by having a controlled drawback of how much martensite there is. So this blue range here is going to be where you form perlite. And let me explain what we're looking at here. We have time here on the bottom in seconds. So this is in 1, 10, 100 seconds. And this is temperature. Unfortunately, it was Celsius. Up here, this would be your critical temperature. And these arced lines here, these are what are called cooling curves. Now you'll notice that this blue is specifically where perlite forms. And you'll notice you're coming down over time. Now, this one right here, you'll see you come down over time and it misses the blue. It's ahead of the blue. And you'll see that if you're ahead of the blue in this area, you're going to form martensite. These lines, on the other hand, you can see they go through that blue. So this is coming down over, this was 10 seconds, and this would be representative of how fast water cools. Okay. Right here, this is your normalizing. You'll notice it's 10 to the second. So that's 100 seconds. That's normalizing. Okay. And then you'll notice over here, 10 to the 4, that's a lot of seconds. We don't need to worry about how many, but that's going to be annealing. That's if you insulate. There's a reason why I'm showing you this particular chart. This is called the time temperature transformation chart, a TTT chart. It's actually TCT because it's got the blue outline. But the point is, you've got to miss this it's called the nose. So this is when perlite forms, and you can see it forms over time. So the whole point is to sort of race past that, and that's going to get you your martensite. I'm going to tie this in with air hardening steels here in a second. People always ask the question, well, how does an air hardening steel harden in air? The reason is because this area that forms perlite is over here somewhere. It occurs later. So it still will occur, but it just occurs later. So you have a bigger window here. Instead of being 10 seconds that you need to race past the nose, it might be 100 seconds, or it might be 500 seconds. Who knows? Every steel is different. So you got to get the chart. It's called a data sheet for each steel. So let's take some of those things, and what do you need to know? This is a generic chart. So you've got time and temp, and you can see there's no values on here. And what you need to know is that austenite forms within a range. There's a lower transformation temperature and an upper. It forms in proportion to how high it is in the temperature. If you're down here, you will not have as much of your carbon go into solution as if you're up here. So you want to be up here without exceeding that. And then you have martensite down here. That's pretty well fixed. It's between 600 and 400 degrees. Okay, and this green is this green here is your cooling curve. So you need to come from austenite down to martensite, and you'll notice it's not a straight line. That's because usually you don't have a straight line from point A to point B. It usually has a little bit of an insulation because of the vapor jacket you're trying to break up. And down here, it gets into what's called convection cooling. So it slows down. But imagine the whole idea is that you need to get to here from here to here in an appropriate amount of time. So imagine that you're in a room, and on the far side of the room, there's a door, and you need to get through that door, but the door is closing. So you just need to get there before the door closed. Now, a steel like water would be like a steel that the door is closing fast. So you got to run because you got to get there in a short amount of time. So you got to run to get through that door. Now, you don't necessarily want to keep running and hit the wall on the other side. You don't want to crash through the door, but you do need to hurry. Now, if you had an oil cooling steel, something a little longer, you might be able to walk before that door closes. And air, you might be able to stop and have a cup of coffee and have a chat. But the point is there's an appropriate amount of time, and the key is just get through the door. And this top line on martensite is what you need to get to from there to there in an appropriate amount of time. So why does this actually matter? Because I know I'm repeating some of what Victoria said, but it matters because air is actually quench because it's pulling heat off of your stock. So it's not normalizing your steel because it has other additions of other alloying elements. It has a higher proportion of chromium and molybdenum, has vanadium, and that sort of stretches out that whole window so you've got a larger window. All the rules still apply. You can still form perlite with air hardening steels. You can still anneal it, for instance. But to anneal it, you've got to have the annealing process go over a 24-hour period in an electric kiln where it's coming down, 15 degrees or such and such degrees over every 15 minutes. So you can't do that in a shop setting. And that's really important because if you're not understanding what's going on, you could make an unsafe tool. You could still have hardness on the struck end. So what that means is, now that we've kind of talked about what's going on, if you heat past critical temperature on an air hardening steel, and air is your quench, then you know that if you get this hot enough, then it will quench. So you can't normalize this or anneal this in a practical way in the shop. And just to emphasize that, like I said, you can get a data sheet on all of these tools, on all steels, right? This is right from a tool steel manufacturer. So bringing this up to critical temperature, look at this range, 1800 to 1890. Well, first thing that you need to notice is that that's a lot higher than what was shown on that earlier chart. That's really, really hot. And you can do as low as 1800. It says air is the quench, meaning air is sufficiently, and this is why that chart, getting back to what Victoria said, sufficiently rapidly is the wording, because there's different rates of cooling that you need for different categories. And tempering, this is another thing that I want to point out, is that technically you should be tempering at 1000 to 1150 and hold for an hour per inch. Well, you're not going to do that in the oven that you bake cookies in, right? So hardening H13 without a kiln. Now I have a kiln, so I can anneal this. So I have a struck end because I can do that, but you don't want to ever heat this whole area up. Okay. And what are the particulars here on here? It's going to harden in air, and you need to heat it to 1800. So how do you know what 1800 is? The best way that I would recommend if you're going to start working with steels like this is, as Victoria said, you want to start with your magnet and know that that's at 1420, and then learn your heat treatment range for normal steel. And you're going to start having to learn how to gauge by color, but everybody perceives color a little bit differently. So you're going to have to figure out how you see the color. To me, I perceive the color as sort of a bright orange, but if you look at the chart, it's not really in an orange range on that chart. Or maybe it is. Maybe I don't perceive color that way. So you can start to ramp it up, but you'll know that it's hardening with H13 if the scale starts to pop off. So scale popping off is a good indication that you're forming martensite. And you always want to have safety glasses when you're working with this steel, because this stuff will fly. But if you don't bring it up to critical temperature and it doesn't have the scale pop off, remember the color that you did, and don't take it all the way up to what you think is 1800 and then just, try to guess at it. Get it a little bit hotter, like a shade hotter than what you would do normal steel, and then let it air harden. If you see that scale pop off, test it with a file, see if it's hard. And then if it's not, put it back in the forge. It won't hurt it. Bring it up another shade past that. Leave it. Now, I wouldn't leave it. I left it on this vise for the picture, but the way I do it is I hold it in my tongs until the scale pops off. And I go through the process of what I would normally do with a quench. And I hold it in the tongs in regular air. And when I get the scale popping off, then I know that it's hardening. So to do this all, to spec, you would need one of these guys. You need an electric heat treat kiln. And that's not to say that you can't work with H13 in a shop setting. You just need to know how some of these rules apply so that you can do it in a shop setting. So one thing is, you can temper at in a regular oven between 450 and 475, and do that for a long period of time, 2 to 3 hours. And then that's going to be your initial tempering. And then if you recall, the tempering that it said was 1150 degrees, 1000 to 1150. Well, you can do either a hotter temperature or you can do a longer time. Both will continue to break some of that martensite down into perlite, which is going to get you your safety factor. So if you leave it longer, then it gives it a longer period of time for it to break down a little bit and add some safety to the tool. So you do a longer period of time. Remember, you can't normalize it, so don't get your struck end hot in the first place. However, just because I want to be extra safe, I'll always use a plumber's torch. And even though I don't get the ends, the struck end hot in most cases, I'll still temper, because I don't know if I maybe had some heat transfer and I just want to be extra safe. Now, you'll remember from the tempering diagram there, it had all the examples of color. Once you get through the blue range and it just starts to go to a gunmetal color, that's 730 degrees. So if you take it up to about that temperature where the blue goes out and it goes to a metal color, a gunmetal color, that's 730. And if you do that a few times, then that's approaching pretty close to 1100. And that's a pretty safe bet to make sure that you're safe. If all of this is too worrisome, if this is too much, then, just use the 4140. That's fine. But if you want to start getting into air hardening steels, just understand that everything you know about heat treatment still applies with air hardening steels. And you just need to understand how to make that tool safe by using air hardening steels. You thought we were done, but there's still one more. Okay, so we've got this corner bend chisel. It's a taper on the end with a bend in it, and the taper is to about a quarter of an inch. You're going to bend it. You can upset into the corner, or you could do a Haberman corner where you use a peen and you draw this corner out, and it's going to fill into the corner. Mark did a Haberman corner. I did an upset. I did mine before I talked to Mark. And then you're going to, draw that out. So you're going to do a little tiny upset, take it to a quarter of an inch on the end, keep a little bit of an open angle from 90 if you're going to upset, or for that matter, just do a Haberman corner. It's your preference, whatever you're more comfortable with. And then clean it up and get it to 90 degrees. And then mine ended up getting a little short, so I had to draw it out a little bit, but then you're going to take it to a little bit of an edge chisel profile. And this is for grooving the tongue. And this has to fit down into the mouth. So here we go. I'm taking it on the off edge, bringing it just above 90 or open from 90, maybe 100 degrees, a little upset, and then cleaning up my corner. Went a little too far, but I have the means to fix that. So I use my hammer like before. Figure that out. And from there, get up a little, then you're going to to the thickness that you need. And then bevel it. I wanted my edge to be straight, so I just need it. And then I ground a little bit of that back so that it can fit into the mouth, and then cleaned up my edges, and then at the end put an actual little edge on here. And that is it for me.